Thanks. Okay, I'll get started. Hi, everyone. I'm Mathieu, and today I'm going to talk about first-class verification dialects for MLIR. But first of all, we need to understand what MLIR is, because not everyone might be familiar with it. So MLIR is not a compiler. MLIR is a compiler framework. It is used to build compilers. And the idea is that in MLIR, you have an IR that is essentially a collection of what's called a dialect, which is an abstraction level in your compiler. And you can extend MLIR with your new dialects, and you can also combine the dialects together in the same program. So if we take like a very simple example of, let's say you have a TensorFlow kernel, you would start with something like a 2D convolution that is in the TF dialect for TensorFlow. You would slowly compile it to a representation that has both arithmetic in it for the add f for adding floating points, but also has an affine for loop that is defined in the IR. Then you would again lower this only partly program to the GPU.launch that replaced now the affine for loop. So the idea is that compared to something like LLVM that has a kind of fixed set of a representation, MLIR has these way more complex different abstraction, these dialects, but also can be used, everything can be extended on all of the sub-projects that actually use MLIR. So for instance, there's the circuit project that had the circuit design that use MLIR. There's TensorFlow for machine learning. There's Mojo for general purpose programming language, or there's Fehr to do fully homomorphic encryption. And because you have such a big ecosystem of compilers, there's a lot of tools that you might want to have in your compiler framework. You might want to be able to do translation validation. You might want to do super optimization. You might want to do something that check if your dataflow analysis is actually correct or not. But all of that requires one central thing, which is to actually be able to define semantics for whatever abstraction you're defining. And this is what we want to have in this project. So there exist already some tools that can define, let's say, a translation validation tool with MLIR TV or a bounded model checking tool on circuit with circuit BMC. But the problem is you cannot really use circuit semantics with the translation validation tool that is defined for what I call MLIR core, so kind of the built-in dialects in MLIR. And you cannot use the bounded model checking tool with the MLIR, and you cannot use the bounded model checking tool with the MLIR core dialect as well. So the problem is there's kind of we had kind of siloed semantics that define only some sub-project and are not really exposed for other people to use. And that's kind of the core of this project is, can we make the dialect semantics actually core component of MLIR? Can we expose them so then we can reuse them for other projects? And the idea, as anything is in MLIR, is to just add more dialects. And this time it's called the semantics dialect, let's say, which allow us to represent kind of semantics, and the same way you would, let's say, MLIR would target a CPU abstraction or a GPU abstraction. Here you would target a semantic abstraction that would represent the actual meaning of your programs. So we would translate it to our semantics dialects and then use kind of what MLIR always does, which is you progressively lower, like before we went from like a 2D convolution to then affine loops to then GPU launch. Here you would also go slowly up to down to something like SMT-lib, so then you can use SMT solvers for whatever tools you want to use. And the idea is that we can build a lot of tools while reusing everything that we've been defined using the semantics dialect, using the semantics dialects. All of it is what I want to say is we want to integrate this in part of the kind of MLIR ecosystem by using dialects, transformation as passes, as compilation passes. And we also create that way a separation of concerns, because we have a compiler expert that only has to essentially create a compilation pass from their dialect to the semantics dialect. At the same time, you have an SMT expert that doesn't really have to think in terms of semantics of programs. You just have to think of the semantics of the kind of semantic dialect, the kind of abstraction it has, and how to actually map it efficiently to SMT-lib. And then you have the tool builder that just have to define tools without having to understand the semantics of all possible dialects that he can use with his tools. So let's get a bit on each of these kind of experts and see how this exact like framework would work. So first, the compiler expert. So the way we essentially do mechanized semantics with SMT solvers in compilers in general is you have your program as input, a division by 8. You have a program as output, a shift right by 3,
and we just want to do translation validation for it. So what we do is that we compile this, so there's an arrow that it isn't really shown. We transform each of these operations into their meaning in SMT. So here division by 8 and a shift by 3. And then we combine them together to a single query that can be passed to an SMT solver. And the thing is, again, if you work with people that use MLIR, the first instinct is, oh, actually, everything is a dialect, so SMT-lib is the dialect. So here we also want to map, the key idea is that whenever we do this translation to SMT, we can just do that inside the MLIR compiler. And that's quite easy because SMT-lib has a simple reference that is based on S expressions, and you just map each constructor to a single instruction in the MLIR compiler, and that's how you define a dialect for MLIR. It's just like very simple. You take each of the constructor in SMT-lib and define an instruction for each of these. So now, if we want to do mechanized semantics through the lowering, through MLIR compilation, which is what we've done, essentially we just call a pass, let's say lower to SMT, that goes from our arif representation to our SMT representation, and that allows us to essentially reuse the MLIR infrastructure to define semantics. And that's really nice because if you can reuse the MLIR infrastructure, that means that you can have compiler experts actually define semantics the same way they would define whatever they do in like their usual work, which is just defining new passes, using the people rewrites that they use in compilers. So that makes them in kind of closer to what their usual environment is. So once we have this, then we can essentially map kind of dialects from their MLIR dialects to an SMT-lib set of dialects. So I separated each SMT theory into its own representation, its own dialect. But the problem is there's sometimes gaps that are too huge. It's how do you translate something like a memref.load, which has to understand undefined behavior, memory, which is quite complex in LLVM. How do we go from a memref, like memory reference representation, to SMT-lib? There's too much big of a gap. So that's why we also introduce kind of a set of high-level semantics that would allow us to essentially simplify the definition of semantics for these dialects, but also, again, as I showed before, creating a better separation for the SMT expert to actually map it themselves to SMT. So the way we can define kind of semantics, this is, let's say, the semantic of writing 42 in memory in some address. And by defining these high-level dialects, you can talk about things like memory effect, where we have here pointers, and then you can do an offset of pointers. You can write in memory, and there's a state that people can use. And you can also talk about undefined behavior effect, like here triggering an undefined behavior whenever you would write in a place that is out of bounds. So this is kind of giving a nice kind of high-level view of a high-level way to define semantics, which is quite nice, so then people don't have to think how it will map to SMT. So now that we have these high-level semantics, we have the SMT expert that can come and say, okay, now it's time to actually map it efficiently to SMT such that the SMT solver will not pass 2 billion years just solving a simple problem. So when we have high-level and SMT-lib semantics, there's two things we want to define. One, which is optimization at each level of abstraction. So there's always things like constant folding and small rewrite rules. And there's also this kind of lowering or compilation path to go from this memory to SMT-lib. So for that, the good thing is that we don't have to reinvent the wheel. We can just use this wonderful paper about SMT encoding of LLVM memory. And the idea is that we take these IDs and we just have it into our own dialect. So we have the memory effect, that we have some optimization, and then we can lower it to memory, which has this block representation that is defined partly in this paper, and also undefined behavior theory, that we also have passes to optimize them again, and then we lower everything to SMT. And the idea is that we can do this in multiple smaller steps, so it's easier to reason about the correctness of what we're doing, and also to maybe find better optimizations, because we're just looking at very snapshots of like, we're working at a very specific level in our abstraction. Another kind of things we can do is just have optimization on SMT-lib itself without having to depend on a specific SMT solver. One very simple optimization we can do is whenever we have a function that takes a pair as input, pair as in using the algebraic data types of SMT, we just replace this by a function having 2 inputs. And when we have a function returning a pair, we would just have 2 functions that return the 2 components of the pair. And that seems really simple, but it turns out whenever we did translation validation experiments, we got 60% speed up with Z3 because Z3 would not handle these algebraic data types as much as we thought they would. And we also reduced the number of timeouts we had on our experiments. Note that this did not apply at all to CVC5, which had absolutely no effect whatsoever because we think that they're actually handling it nicely. So now that we have the semantic dialects, we have a way to map them to SMT, we can actually start building tools around that. So we built 3 tools, a translation validation tool, a pass verification tool that relies on verifying people rewrites, and a data flow verification tool. And the kind of idea on how you would build this tool is that, let's say you start with an arith program, so a program based with the arith dialect, so just simple arithmetic. You compile it using, you apply an optimization pass, let's say just a canonicalization pass, something that do simple people rewrite for optimization. And then we reuse our kind of lowering to or compilation pass to the semantics dialect. And then we just merge them together, apply some semantics optimization, and we found some bugs in MLIR like this. It's just like a simple way to write a translation validation tool by just reusing the components that we can have. And if we, instead of using arith, we would use something else that has a mapping to semantics, then we can use the exact same tool and it would just work. Another tool we can write is, so the people rewrite verification. So there's the PDL dialect in MLIR, which is kind of a meta dialect to represent rewrites. So we have, for instance, x plus y. So x and y being 2 operands, 2 value rematching. And we want to rewrite this to y plus x. And it's just like we replace y plus x with x plus y. And so we use a program like this that represents a rewrite. We compile it to the semantics dialect by using the semantics of, let's say, something like arithmetic for the add. And then we apply the semantics optimization, and that way we can kind of verify people rewrites. I'm not going to go much in detail about it, but essentially it's a very simple one-to-one mapping where we have to kind of recursively call a pass in order to give the semantics of things we match and things we rewrite. And we kind of, in the paper, we show that we can essentially prove a canonicalization pass both for the comp dialect in circuit and the arithmetic dialects in MLIR proper. And finally, one last thing we do is that we build a tool to do a data flow analysis verification. So we check that the transfer function for a particular operation is correct. For that, we added our own dialects because in MLIR you can always add new dialects when you need them. And we added one to essentially represent known bits analysis and demanded bits analysis. And we define our own transfer function in MLIR so that then we can use to verify their correctness. So we just take kind of the semantics of a comp program, the semantics of a transfer function, and then we just like kind of combine them to prove their correctness. So in conclusion, we define kind of a set of semantic dialects, not only a single one, that allows for compiler expert to efficiently target target like a semantic meaning, give a semantic meaning of the programs the same way they would target a CPU or a GPU target. And we also define a set of semantic optimization, and we allow people to use the MLIR framework to build their own optimization and efficient lowering to SMTlib. And we have everything that is working in MLIR, so we can reuse the MLIR infrastructure. We build a set of 3 tools that we present in the paper. And this allows essentially a better separation of concerns for everyone involved to essentially be able to define better, define semantics for MLIR, but also use them for nice tooling. And thank you. And if you want to know also more about this, we have an MLIR compiler workshop in September, and part of it is going to be about the semantics. Thanks.
All right, questions for the speaker? Looks like we have one up front here and then one in the back.
Hey, thanks for the great talk. This is Rajat from MIT and Jane Street. I was curious, so the design of the semantic dialects seems tailored to the particular kinds of subdialects from MLIR you have picked. So for example, arith and comp comp is just sort of the purely mathematical subset of a circuit that you take. Those seem very nicely able to fit into the SMT dialect. Have you thought about what it would take to embed languages or dialects with more complicated semantics, like dataflow semantics or temporal semantics, like the HW dialect in circuit does?
Yes, so for now, everything, so there's, first of all, because we're using MLIR, there's already problems if you use anything that has generic dependent types. That's like something that's quite hard to represent in MLIR is itself. Otherwise, we're thinking of things like tensors, which are also quite complicated because it's hard to fit them into SMT. And the idea is that with the way we want to define things, you would have to define kind of over-approximation of the semantics. So you would have to say, oh, I know that this thing is commutative, so this is like, we can check for certain properties, but we won't be able to have like exact check that something is correct or not, if that makes sense.
So it's sort of things that fit nicely into SMT are the things you will
for now it
support
has
currently.
to fit something that you can pass to SMT.
Okay.
Or if we had, if there is like other mathematical language that you can actually have decision procedure, it would be something that fits these decision procedures.
Yeah, thanks for the great talk. I think it's a really great idea to can embed the compiler with this semantic, but I agree that having semantics will help you to build a toolchain, but sometimes there could be no consensus what the semantics should be like. And I think what people do in this situation is that they only define the portion of the whole semantics. So my question is, do you think it's possible to build some toolchains that only defines the portion of semantics and just leave the other semantics just undefined?
I see, that's interesting. So I'm trying to think, it's kind of this idea of having an over-approximation of semantics, right? Is saying that in these cases, you don't exactly know what happens. And I'm not exactly sure how you could do this, but I'm not exactly sure how exactly it would fit in the system, because if you really say, I don't know what happened, that means it could either be undefined behavior or it could be exactly not undefined behavior. So one thing is, because we represent everything as a pass, you could have one pass for one semantic that people agree on and one pass for another semantic that another group of people agree on. And you can like kind of choose the one you want. So that's one thing that we can do.
Okay, thank you.
Yeah, thanks.
I'm Charit from UIUC. So have you thought about like building using existing semantics for stable HLO or HLO like in this?
This is one of the next thing we're looking at least.
Yeah, so there's some existing work on formalizing HLO. Like, did you think about like using that?
So we haven't really looked at it yet, but we should definitely talk then.
Okay.
Okay. Thanks.
All right, let's thank the speaker again.